Okay, so there's a question on question 4 of the previous exam, right? And so I'm just gonna go off my head for a minute here. But this question, right, looked something like this, and you can correct me if I'm wrong. But we had an applied F app in the middle, right? And we also had a distributed load, right?
Yeah.
Okay, like this. And we said it was of magnitude W, right? That was pretty much what we're looking at. Okay, so for the first part, you can actually, the first time I did it kind of together, okay? But you can separate them like I've got them here and do superposition. Maybe let's go ahead and do them separate for now, and then we'll go from there. All right. So in this case, I've got a reaction. We'll call it MF. Okay, and we'll call this one RF. All right, because it's dealing with the F app. And then on this one, we'll say that we have an MW and we have an RW because it's dealing with the distributed load. So I'm going to go ahead for now and just make that a concentrated force, right, which is going to have magnitude of WL, and it's acting, you know, across. But at least we're doing the external equilibrium, which is the first step. We'll do it this way, right? So what do we see? We see that the RF will equal the F app. We see that the MF will equal the F app times L over 2. And we see here that MW, well actually let's I guess do RW first. We'll see that RW is equal to WL, and we'll see that M sub W is equal to WL squared over 2. Does this all look right? I'm doing this off the top of my head, so I hope it's correct. So that's kind of the first part. And then I asked you to use the differential integral relationships, right? But even in that step of using the integral differential relationships, it's a good idea to still look at the boundary conditions. Okay? So on the left side, right, I have a little squiggly, I have my MF, I have my RF, and then I use the convention, right, for V, and there's M, and I can do the same thing over here. Right, and so what we see at the left side is that the V, right, is going to be equal to RF. Over here, V is going to be equal to RW, okay, and I guess we can say that this is F app, and this is going to be WL, okay, and so with superposition, we can see that the internal V is going to be equal to this F app plus WL. Okay. Now, at the right side, oh, I guess we can do the M as well. So we see that, okay, the M okay, at this left side is going to be equal to minus mf. We see here that the m over here for the w is going to be equal to minus m sub w. And so the m at the left side will be equal to minus mf minus mw. And so this means that we're going to be down at, well, if we want, we can take the, I don't think I did this in the solution necessarily, maybe I did, but it's going to be like a minus L over 2 F app plus WL, something like that. Did I make any algebraic mistakes yet? Okay. So this is the boundary condition at the left side. For the right side, we have something interesting, maybe. So we use our convention, right, that we have a V going up internally, and we have M like this. And for both cases, if we look here and here, there's nothing going on at the right side. Right? There's no no constraint there. There's no applied force. There's no applied moment. Okay, so for both of these cases, what we see is that M, or we'll say V at right side, is going to be equal to 0, and M at the right side is also equal to 0. Okay, so this, we hadn't even gotten to the differential integral relationships yet, but we've got an idea of how this system is going to behave slightly. All right, so let's go ahead and draw out a shear force diagram, and we'll get back to the bending moment diagrams in a little bit, okay? But we'll work on the shear force diagram right now. So for this, we see we have a concentrated F app, right? And that's going downward. That means that at L over 2, right? So we see with the F app, let's do something like this. We expect that we're going to have a delta V equals minus F app, right? Because that's what happens to the shear force according to having a concentrated force there. And we also know that we have our lovely dV dx is equal to W relationship, right? So this means that V is equal to integral of W dx. Now, we have two scenarios, or we can think of them as combined if we want at this point. We have this case where we have a W and it's negative, and we have F app, right? Well, F app is not a distributed force. So in reality, across this, what we're going to have is, okay, V is equal to some integral minus W dx, right? Which is going to give us a minus Wx, we'll say, plus some constant, something like that. Okay. So this slope is the same across the entire span of the beam. And we have a discontinuity here. And we know that at L, okay, we're going to be at 0, okay, for the shear force, because we said, well, look, there's nothing going on over there. And we know on the left side, we have this FAP plus WL. Okay, so we can go ahead and we can say, all right, well, at 0, we're at this FAP plus WL. Okay. And then at L over 2, something weird is going to happen. Okay, why? Because we said that there was this delta V of minus FAP. And we know we have a slope of minus W x plus C1. All right. Now, if we look at the left side, so there are a couple ways to look at this. One is, all right, I can look at like an x1. You know, I could put in something like an x1, okay, until I get to the middle, and then I could put in an x2 here, okay, because I have two separate kind of boundary conditions I have to satisfy. You could look at going from the right side and making like an x3. That makes things a little complicated, okay, but it could be done. And if you do that, then the slope would be flipped because you're going from the other side. But graphically, all right, what we can think of is there is some, forget the constant for a second, there is some slope minus W. Okay, so if there's a slope minus W, at L over 2, I will go down from L over 2, whatever I started at, I will be at minus, I will have a deduction of minus WL over 2. So I can actually kind of say, oh, let's just say that right here, because I know I have a slope, okay, I've been going and I've lost minus WL over 2. Okay, so what does that mean? That means that the value here there is going to be FAP plus WL over 2, because I lost, right? It's a linear, right? And I can even say that this has got slope minus W. Okay. What happens here? Well, here I drop an FAP, right? We said, oh, right, there it is. Okay, I drop an FAP. So at this location, we have a delta V equal to minus FAP. Okay. So now, what does that mean? That means that my value right here is actually just WL over 2. And this is awesomeness. Why? Because I know I have a slope again of minus W. And guess what? I had to get to 0. So I go over 2, and I've got that nice slope. Like that. That was maybe not the bestest. Let's try a little better this time. Okay, like that. This also has slope of minus W. All right, and that's the approach to figuring out the shear force. Okay, now let's talk about the bending moment. Okay. So for the bending moment, I do think it's easier to think about these in two separate cases, right? So we have our F app and we have our W. Okay. With the let's look at it. You know, this is let's say analysis. How do we say analysis for F app case? It's probably not bad, right, to think, all right, we've got nothing going on here. We have a change in the F app, all right, and so, you know, if we do the integral of for v, right, v is equal to integral w dx, but this is just going to be 0, so it's going to be some constant, all right, like that, something like that, okay? Now, it's okay, let's say, to not forget what we know how to do very well. And that is take a slice, right? I know we're saying we're using differential integral equation. We'll use that, all right? But here, I mean, we can go further. We can say that we have an m is going to be in some type of integral of c2 dx. And so, yeah, we know that we're going to have some type of slope, essentially. We're going to have some type of slope. Now, what is that slope? Well, we've got to satisfy some type of moment at the left side, and we already said that at least due to f app, it's just equal to minus f mf, right? And we said that mf is f app L over 2. Okay. So another way, you know, this is where sometimes it's not bad to like say, oh, you know, let's just use the basics. Here's my nomenclature, here's my m, and here's my mf, here's my rf, okay, like this, and I already know what v is. V we calculated out, right? What is m? Well, let's do m at the left side. That way we get rid of rf. So let's say, you know, summation of moments at left side. And when we do that, what are we going to have? We're going to have essentially just mf plus m, and then we have a minus xv, okay, is equal to 0. That's when we sum it. Okay, so v, and in this case, right, the v was just going to be, at least from what we have here, it's just it's a constant, right? Because as we go along here, right, if we come back to this, it's just going to be a constant RF until we get to the discontinuity. Okay. So this is going to be MF, which is F app L over 2. Okay, plus M minus X times F app equals 0. So now I know that my M is equal to, let's see here. it's going to be equal to f app x minus L over 2. Okay, if I did that correctly. Yeah, because it starts at minus, and that lines up with this boundary condition that we have right here on the left side. Okay. So what does that look like? That looks like a system where this is x, this is the positive moment. We start off down here, we get to L over 2, okay, and it has a positive slope of f app, okay, but it starts down here at minus f app L over 2, so this is minus, okay, and then it goes up to here. All right. Now, if I'm in this portion, all right, I'm in this portion, then I look and I say, oh, what's happening between here and the end? And I have my V up and I have my M doing the smiley thing. There's nothing going on in this region. There's no internal bending moment. So this just continues and is flat. Like that. Okay, and that's it. Now, for the other case, all right, and for the sake of time, I'm gonna skip this because it's in the notes actually. All right, but if you look at the notes, for W, all right, what happens there is this goes that like that. It essentially starts down here, and this is going to be minus WL squared over 2. And it ends up at 0, and it's a parabola. Okay? And that's because, right, this has no discontinuity in it, so it's actually a little bit easier in some sense, right? But the first integral is going to be minus Wx, all right, plus C plus a constant. And the next integral is going to be minus 1/2 Wx squared plus that constant times x plus another constant, okay? And so that ends up being quadratic there. Okay, any questions on that? And you can take a look at the notes. That one's right there. That one was a little more straightforward. I think this one was the one that actually threw people off, and really I know I said use the differential integral relationship, and you can kind of see what's happening there, that it's going to be a straight line. You can also, when in doubt, especially with a concentrated force or something of that nature, go back to what you would do in statics and make sure that it makes sense. Okay. Okay. Kavya, did you have a question you wanted to ask? Huh? You can wait till after class? All right. Were there other questions? Yes.
I just wanted to confirm the first moment graph for the f app.
Mm-hmm.
Does the moment, there stops being any sort of moment after L over 2 because after that second half, there's nothing for any moment to react against, right? If that makes sense.
You're talking, so like once we get, yeah. So like that's when you look at it and you say, oh, if I slice right here, there's nothing happening. There's no external force, no external moment, right, on the right end, and so it's just those have to be 0.
Makes sense.
Yeah. and they have to be 0 as this continues on to the right. Okay, good. All right, other questions you want to cover before we get into the new material? Okay, well, it is time for class, so let's go ahead. Today, we're going to have our 5th session on beams, and tomorrow we'll have our last session on beams. This session represents the last material for which we might be responsible for the exam, okay? The next one will be kind of for fun. Well, not for fun, actually, it's part of, kind of, I think, what people would expect that you've covered in the course. Right? But given the proximity of the exam to that assignment and content, we're gonna say hold off on the exam at least. So, oops, wrong one. We're going to think and derive equations that describe the deflection of a beam as we go across it. So, through your practice as an engineer, you're really going to just flip open the internet. Well, before you would have a textbook, and you're welcome to use Hibbler's book. It's a great book. Okay? If you flip to the appendix, you'll see that there are a bunch of tables, or there are tables that have a bunch of different configurations for beams, and they describe what the deflection is across this beam. The deflection and also the slope, okay? So the deflection is given as a V, all right? In our case, V is positive upward, okay? So our deflections are going to be negative if the forces are acting downward on them. And so you get this, you get the deflection, and you also get the rate of change as you go across as a function of x. That dv dx is going to be a slope, okay? And we'll also talk about the procedure for calculating deflection, all right, without these beautiful tables. And then we'll do another finite element example, okay? Kind of following what we might consider to be the ways of an engineer too. So the first approach is going to be go to the back of your textbook that you might have, or go to the internet, look at the tables. If you can, use one and then get a general idea of what the deflection is across the beam, or what the max deflection might be. After, of course, that you figured out what the maximum bending stress is, and if the material is going to fail because of the transverse loading that you have on it. And then you can go to finite element analysis and confirm what you have in those tables. Or you can have a more complicated geometry than what you had in your tables. So why do we care about deflection? We might need to meet certain functional requirements. If the material is brittle, deflection or extension could lead to cracking and failure. And further, you might ask yourself the question, is it possible to go from deflection to stresses, okay, or vice versa? So what are we saying there? We're saying if you saw a beam, okay, I don't know, it's probably not something that you're going to do a lot, but if you saw the deflection of a beam, could you then back calculate, like we did with strain gauges, what the state of stress is in that beam? Wouldn't we like to be able to calculate the spring constant? Okay, so in 439 in multi-physics, I've introduced using finite element analysis to do calculations for a springboard. Springboard and the Olympics are coming up. All right, I don't know if they start, what, in a few weeks? Is it a few weeks? I don't know. But you can kind of calculate, hey, what's the spring constant of a springboard where they're jumping off? Now, why does a springboard why do they even use a springboard for diving? Or anything? Why would you use a springboard? How does a trampoline work? And I guess essentially what I'm asking is, how do these trampolines or mechanisms, like diving boards or springboards, how do they propel someone higher than if I'm just jumping off the ground? Yes?
I'm just gonna take a guess. It's the combination between your normal force from jumping off a surface, but also the force that it creates as it's trying to return back to its original position after you deflected it.
Okay, all right. So if I am just like, don't we have conservation of energy? Right? Like, how can it send me higher? Yes.
I would say that it allows you to store the energy from your first jump, and then you can add that to your second jump, so that you're jumping basically twice as high.
Yes. All right. So if you look, the springboard divers, they do multiple jumps. Right? They will come to the end. They'll come forward, and they'll jump, and then they can jump again, and maybe even jump again, and they'll get themselves very high because what they're putting more energy into the system by bending their legs and shooting off. Right? So they're able to store that energy, and there's a conversion, of course, between the kinetic and the potential energy. Okay. So yeah, you might want to be able to calculate a spring constant. Now, a spring constant is going to be dependent, right, on the location of the beam and the configuration of the beam, right? So in this case, this kind of looks like loading in the middle, right? So that these ends are must be somewhat fixed based on what we're seeing here with this curvature, right? And so, the spring constant might be between the applied force there and the displacement, so at the same location. Maybe in another situation, right, we have a springboard where, it's fixed here, and there's force being applied here, and there's a delta going downward. And so maybe that's another type of diving platform or whatever. And the springboards, I guess, the way the Olympic ones work, from my understanding, and I'm not a diver, okay, they look kind of like this. They have a pin at one end, and then they have a roller, okay, and then the diver can actually adjust where this roller is, okay, relative to this pin or relative to the end. Okay? And a lot of times, I believe the more experienced divers, they roll it back further. Okay, so this is something that we'll be able to understand. And another thing that is interesting about being able to calculate effective spring constants and masses is that we can think about vibrational resonance. Okay? So you remember from physics, or when you take a class that focuses on ordinary differential equations, what an underdamped second order system looks like, right? Does this look somewhat familiar? That little poor sketch I made. Okay. Does anyone remember what or how you predict that resonant frequency? Let's do a thought experiment. If I very, very, very thick cantilever beam, will that have high stiffness or low stiffness? High stiffness. All right. And if you were to flick it, it goes, okay, versus now I have another beam that's thinner but has the same length, and I flick it. Which one of these is going to resonate at a higher frequency? The thick one or the thin one?
The thick one, right?
Yes, the thick one is going to resonate at a higher frequency. That's correct. Excuse me. Okay, so it goes. It's related to the stiffness. Okay, now let's think about a mass sitting on a spring. Okay, so now different system. If I have a given spring constant and it's sitting on the spring, I have a given spring constant. I don't change the spring constant, and I put a light mass on the spring versus a heavy mass on the spring. Which one of these is going to vibrate at a higher frequency? Same spring constant. It's like I just put it on a, or I go to the grocery store, and they have the little scales on the springs. Okay, if I put a big mass on that scale, is it going to vibrate faster or slower than if I put I put in a watermelon, right, versus a grape? Which one of these is going to have a higher natural resonance frequency? Yes.
The watermelon.
Okay. Actually, it's the opposite. All right. Yeah. What are you thinking, Dylan?
It's the smaller one. I think I just remembered the formula. Isn't it like square root of k over m?
Yeah. All right. Okay. So the omega n is equal to square root of k over m. All right. So now, if you have a beam, right, and we can calculate its stiffness, and we have kind of an effective mass for that beam, okay, we can figure out what its resonant frequency will be. And you could have something like a tuning fork, which is a couple of these cantilevers working together. I've told you about the washing machine, right? I told you about the washing machine? Okay. How do we get through a whole semester when we're not talking about the washing machine? So, why is a washing machine wishy-washy? And I'm talking like top loader or front loader, right? So I think in schools now we have mostly front loaders, right, in the dorms. But anyway, you go in there, right, and you grab the middle cylinder and it's like, right? Has anyone ever done that? If it's a top loader, or if it's a side loader or front loader, right? You're like, this big cylindrical thing is like, woo, woo, woo. Why in the world would it be wishy-washy in a washing machine? Yes.
Because of the clothes, because of the rotation of the clothes, like pull out. You get what I'm saying? Like, yeah, I don't know how to listen.
So like, okay,
Like the force of the clothes.
the force of the clothes, like it might have an imbalance for the clothes, right? Okay, and so I want to make sure that the washing machine doesn't walk away, right? Because if I've got an imbalance, an eccentric mass essentially that's spinning around, right, and I have some omega, then I get some acceleration, omega squared r, and the radius of that thing. Yeah, I don't want it to like vibrate to death. Okay. So why in the world did I make it wishy-washy though? What would your choice be? If you don't want it to vibrate away, what would you do as an engineer? Yes.
Does the the force of the clothes against the wishy-washy area kind of act like, I forget what it's called, the waves that cancel each other out.
Okay, yeah, you
Cancel
could.
out some of the vibrations caused by the washing machine.
Okay, all right, yeah, all right. So you could think about how we're having some out of phase cancellation of waves, maybe. Okay, yeah. I mean, at some level, you're right. What does that have to do with the wishy-washiness? Yes.
Since a stiffer object, like a stiffer diving board, resonates at higher frequencies, this makes it less stiff.
Okay. Yeah. So it's less stiff. That's true. It's less stiff. So what does that mean? So go a little further with that analogy. If it's less stiff, then what's happening with the resonant frequency?
The resonant frequency is much lower, right?
Right. Now why would I want a low resonant frequency with a washing machine? I'm spinning fast, right? I'm spinning fast. I want to make sure that I am able to kind of dry the clothes at the end of the cycle, right? It's wet, and then I spin, I use centrifugation with the hose to get the water out of the clothes. So that's when I go the fastest, and that's when I have the highest chance of vibrating myself to death. So why? So we go back to the question, why? Well, what does this plot show here? This is resonance, right? X, or magnitude of X, represents what? It represents the amplitude. And this is assuming that I'm applying some type of sinusoidal excitation. Remember, you had the homogeneous second order differential equation, and then you have the homogeneous equation, but now with a force term, right? So like you've got some type of, either step input or you've got an oscillating input, right? And you're like, oh, I wish I was just seeing a homogeneous form, right? Or I wish I did not homogeneous. So what does this graph say? Magnitude of X is the amplitude. And at resonance, right, everything goes bonkers. That's what happens to the peak. What happens after resonance? The amplitude goes way down. Way down. Okay? It goes down, if it's a second order system, it has a slope of -2 on a log plot. Okay? Alright? This means that every decade you go. So like if I go up in 10 hertz, I drop in my amplitude by a factor of 100. I'm sorry, if I go up in frequency by a factor of 10, okay, so if I go from if the resonant frequency is at 10 hertz, and I go to 100 hertz, I then have dropped, if I was at 1 before or 2, I will be at 2 over 100, my amplitude, okay? And this continues. So the reason why we have wishy-washiness in washing machines is because we're actually trying to cancel out that vibration like you were saying, okay? And it's because of this mass spring damper property, okay, that the amplitude is going to go way down. So if you ever watch a washing machine, you go home, and when it starts that spin cycle, what are you going to see? You're going to see, right? There's going to be a moment where it hits resonance very quickly, and you'll see the machine kind of wobble, and then it just becomes very, very still. That's because we went through this resonance, which is programmed to be at a low frequency. Well, not programmed, it's designed to be at a low frequency. The machine is programmed to go through that quickly and not stay there. If it does, then you've got craziness. One time we had a washing machine. I think it was a washing machine. I don't think it was. No, it was the washing machine. It was installed, and when they ship it, they actually sometimes have supports, rigid supports, to keep it from being wishy-washy while it's traveling. And the people who installed it forgot to remove the wishy-washy, or forgot to remove the supports. So that washing machine, when you ran it, that thing started cranking and made a ton of noise and looked like it was going to blow up, right? So what had to happen, they had to come back and had to remove the supports. And once they did that, then it behaved normally. Okay? So stiffness is not, what's the point here? Making things stiffer is not always the solution to your problems. Look no further than the suspension on your car. All right? I can go over to the side of a car, right, and I can push up and down, and if I let go, it's going to, right? Real slow, very slow. Now there's a damper in there too, right? I've got not just the spring, right? I've got a dash spot in there, so or a shock absorber, right, in there. So that's that, but nonetheless, that is another example where it's given a pretty low resonant frequency, so that when you're going along the road, right, you don't feel it as much. I guess unless you want to feel it, then you can, I don't know, make a hot rod or something, or change your suspension. Okay. All right. So anyway, that was a little bit of a tangent. Now we get to the technical stuff. So here is the sign convention, or some sign conventions. Here are some sign conventions for beam diagram. W, up, positive. Delta F, up, positive. Okay? You know, we're going to say that, yeah, that this, as this delta F goes to delta F over delta X, and delta X goes to 0, then, yeah, this is going to be positive, right? For the axial load, you already know this. And typically, we don't have beams that have axial loads, but you can handle them, right? Why would we want to handle them? Well, maybe to make a crummy question on an exam, where we say, oh, yeah, you know, I've got a bending stress, and it's, you know, in tension on one side of the beam, and it's in compression the other side of the beam. But now I add a force, right? And so maybe that force adds to the tension bending stress, right? Because it's going to add an axial stress, while it makes the negative compressive bending stress less negative. I don't know, right? We could do something like that. Okay. But you know how to handle these situations in terms of calculating out also a stress and a displacement or strain. Okay, and then here these are the similar bending conventions that we've used in the past. And what's going to be next? A shear force, right? Okay, so those conventions, they all stay the same. Now, one other convention is going to be related to, so and then again, I was confused because the book I used, CDL, this one down here, did not agree with Hibbler, this one over here. Okay, so the other thing here is that typically we think of a deflection, right, as being positive upward. That's a Hibbler convention. That's a Hibbler convention, and you'll see that some of the sources that we use from the internet, they don't use that same convention, all right? So again, this is when it's a good idea to put your thinking cap on before you delve into the problem too much and know, okay, I expect this is going to go downward. And that means that by convention, that V would be negative, right? Or I'm going to think it's just downward and I don't care, all right? All right, then getting to the constraints there's a free end which has no constraint on displacement and no constraint on rotation. So now rotation, that's going to refer to the slope. Right? So remember, we have this deflection, and then now we also have, I don't know, let's just say it's going off like this, and this is x, and it, you know, it's bending like this. Now we also have a slope. Okay. Right, can you see that? Like if I were to like draw something like that, you can see, right, that here, I can't even do it right. Oh man, hold on, let's try again. Okay, like here, that would give me a theta. Okay, and that's because I got an x, I'm going x, right? And this theta is really just this d delta dx. Okay, and in our nomenclature, we're going to start introducing this little v, not new. So I don't know how you, and it's kind of confusing. It's not new, it's not the big V for the shear force, but it's a little v. Okay, so that's going to be what we use for deflection. So this is often written like this. Okay. There on a free end, yes. So there's no restraining force, and the curvature can actually be 0. It is 0. Okay, at the free end. So what does that mean? That means if I'm looking at what's happening, okay, once I get to the free end, even if it's coming off like that, crazy like, at the free end, okay, that slope, well, that's really kind of crummy. That free end is going to have 0 curvature. So if I'm thinking about, there's a, you know, before I have something like this, okay, so that would be like a rho, okay, and that would be the radius of curvature. Okay, that rho is like infinite. Okay, it's and it still has 0 curvature. And we're going to talk more about curvature in a minute. Pin constraint. Okay, so pin constraints, they also do not constrain rotation. Okay, they just constrain displacement and they provide a restraining force. So that's what you have in these situations. All right, so this is going to be really, really big there. Okay. And then the last is the fixed wall constraint. So this does constrain rotation, okay, and it provides a restraining force, and it provides essentially a restraining moment as well. Okay, and we know this from our experience. So here, in this case, what you're going to see is that there are two things. V is going to be equal to 0 at the left side, and we also have coming out of here that dV dx is equal to 0, right? That's the theta. So whenever you're coming out of a wall, when you're coming out of the wall, this is going to be 0. Comes out at a 0 slope. Okay? Or you're going into a wall, comes in a 0 slope. Any questions on this? Okay. This curvature being 0 does not mean that it's like here, right? This is a pin constraint. So, you know, you can have curvature in here, right? But it's just saying that at the end. We're at the free end. Okay. The elastic curve is what we use to define the deflection along the longitudinal axis of the beam, passing through the centroids or neutral axes. Okay, so that's what we're talking about here, that this was a longitudinal axis. Right, and so we're thinking about how that moves up and down. Okay. So now let's talk about curvature. Curvature goes with the sign of the internal moment. Positive internal moment, positive curvature upward. Negative internal moment, negative curvature downward. So what are we talking about? Look, this is positive, right? Very happy, smiley, positiveness. Okay? And if I took, a slice there, if I took a slice of this, I've got this here, and by convention I use this here, right? And we see that, this is m greater than 0, right? So the internal, remember, when we think about the strains and the deflections and things, we're often wanting to make sure that we have an idea of what the internal shear force and the internal bending moment are as we go across the beam. So this is a positive curvature. And so positive moment. So positive internal moment means positive curvature upward, right? And we can see this, like that. And what does that mean mathematically? That means that there's a center of a circle that's being carved out, and that, as you're moving along, the curvature can be changing. So, at one location the center's here, at another location the center's there, right? It can be changing. Nonetheless, that point 0 or point O, at the center, is above the beam. Okay, and that's what we consider to be positive curvature. So positive moment has positive curvature. Negative moment, like this, okay, has a negative curvature, okay, which is below. Now, remember from your calculus days, and you're like figuring out your, local minima, local maxima. What was curvature related to? Yes, Javier.
Well, the function.
Okay, the function, right? And okay, calculus. So if I were trying to figure out a local maxima, right?
Critical points.
Huh?
Critical points.
Okay, critical points, right? So critical points would be related to like the first derivative, right? And I take the second derivative, right, to figure out if I were either positive or negative. We're going to do a similar thing here, okay? We're going to be looking at the second derivative, and if the second derivative, as we go across, right, so we already talked about v, right, and that's like the function, that's like a displacement function, right? Then we talked about the first derivative, which is a slope, right, dv dx. And now we're talking about curvature. This is going to be the second derivative of v with respect to x. Okay? So what are we, well, I guess we have a little bit more. Let me just see here. We have a little bit more to talk about in terms of the qualitative nature. Okay. Yeah, so we see here, this is what the shear force diagram looks like. Okay, and this right here is the bending moment, right? And you see the internal bending moment is always positive. What is this profile? I mean, we know that this profile is kind of going to go like this, right? Like that, right? And so again, if we look at our shear force and our bending moment diagram, just qualitatively at this point, it's always positive. So this is always positive curvature. Okay. And there's a displacement, right? So similarly, right, even if I offset this applied force P over here, right, I get a different shear force and I get a different bending moment diagram, but they're all positive, and the displacement is going to look something like this. Okay, still always positive. All right, now we want a relationship, okay, between the radius of curvature and the bending moment. Shear force also contributes, but it's generally not that big a deal, okay? And we're going to be thinking about moving along a longitudinal axis, and we're going to have a bending moment, and we're going to have V being the positive upward displacement, okay, like we see here. So we've kind of set the stage. Well, let's take a look at a beam and a few designated points on the beam. So we have A, B, C, D, E, F, and we're going to talk about our radius of curvature, our neutral distance from the neutral axis, and a bending moment. So in the undeformed case, we have what we have, all right? It's like straight across, as we see here, and we can pick an element in that beam that would look something like this, a poorly drawn rectangle. And it has some width delta x, and we know that we have a neutral or longitudinal axis, and we can think about some distance relative to that longitudinal axis. Okay. Now, the length of this dotted or dashed line going across is going to be delta s. Okay. And right now, okay, without any bending moment being applied, we see that delta s is equal to delta x. They're the same. And I think you can see where this is going, right? What happens if I apply a bending moment? Well, this element is going to change its shape, okay? And let's apply a positive bending moment so that now it becomes a deformed shape where this point and this point are closer to each other, as we see here, okay? And maybe this point and this point are a little farther apart. Now, there are a few things we notice. One is that we can carve out a portion of a circle, and there's a center, and this has some angle associated with it. Two, we can define a radius, okay, as a function, all right, of where O is and the neutral axis is or was, and we can think about how delta x has not changed, okay, on the longitudinal axis. This is a profound point, and I think we've talked about it a little bit before, okay? But this radius that we're mapping out, yes, it's curved, but there is, along the centroid, there is a longitudinal axis, a location or a plane, however you want to describe it, a line where this distance from here to here is the same as it was originally. And so the longitudinal axis or the neutral axis, and depending on the textbook and how it's written out, has another significant meaning. And this is kind of neat, right? We already said that the bending stress there is equal to 0. Well, 0 bending stress, 0 strain. It doesn't change its length, so it doesn't stretch here. And if we go up or down, okay, away from the longitudinal axis, then we're going to see some change in the width. So now we get to what we'll call a delta S prime. Okay. So you can see that as you increase y, your distance from the neutral axis, the delta S prime, okay, that would be shrinking. Okay, that would be getting smaller. So, you know, you can begin to think, oh, well, guess what? This is all circular business, right? Rho minus y. Okay, so I can kind of start to come up with relationships between rho delta theta, right, is equal to this length, the arc length. So everyone see that? And then whatever the distance is from this line to the O, okay, times delta theta will equal this delta S prime. Okay, so we can begin to map out what the effect of a distance y from the longitudinal axis is on delta S prime. And yes, this is with a positive bending moment. Okay, so we have compression and tension in beam bending. And we'll get back to things. Can you see this just graphically? You already knew this because we said when we think about calculating bending stresses, let's not think too much about the negative ny over I, the negative sign, right? We said let's think more about, does this make it a negative or a positive? So now, what we have here is A1 and B1 are closer than A and B were. B1 and C1 are closer than B and C were. D1 and E1 are closer than, or D1 and E1 are farther apart than D and E were. Okay? And so we can begin to see that above the longitudinal axis, with positive curvature, we have compression, and below the negative, below the longitudinal axis, over here we have tension, and we have extension. And we're going to relate those to the radii that we have going to a particular distance above the neutral axis. So here's a deformed bending element. That's just copied from what we had before. And here are a few equations, all right? So at a location specified by distance y from longitudinal axis, we can come up with a strain. Oh, well, that's cool. Remember, strain is change in length divided by original length. Well, we said the original length was delta S or delta X, right? And now the change in length is going to be this delta S prime minus this delta S. And that was 0, or that's that limit of delta S was 0, right? That's going to be the strain. So then we do some substituting, right? We say, oh, delta S prime is equal to quantity rho minus y times delta theta. And we do a little bit of algebra. Okay? And we get this expression for the strain. And then this and that knock each other out, and we're left with minus y over rho. And that is going to be the strain along the beam. Now, it turns out that we don't really care that much okay, about this quantity when we're doing these things, but we're going to build. We're going to build on it, okay? We do care, okay, about figuring out what a relationship would be between the moment and the curvature. So now we have an arc length, okay, right? And then we figured out what the strain in that arc would be, right? So these is an arc. ds, right, is rho d theta, right? So that was, the original dx ds, right? So now we're kind of making things into more differential equation-like form. ds prime is equal to rho minus y times d theta. And then if we combine these things, yes, we get that. And now, we go to Hooke's law. And we have a flexure formula. And we combine these principles to each other. And we get 1 over rho is equal to m over di. Now this is almost in the useful form we're going to use it, okay? But we have accomplished our goal. We have a radius rho, and we have a moment. And we have material property E, and we have geometry property I. Okay? Curvature, right, is defined as 1 over radius. Okay, so 1 over rho is the curvature, and then we have moment on the other side. So now, we've got a relationship, if we want it, between curvature and moment, and we've also now we're able to relate the curvature to stress, if we want it. Okay, so again, now if m is positive, right, then rho is, or the rho is positive, okay, and the center is going to be above the beam, and the rho is also going to be above the beam, right? So that we knew, and we also have an idea that since these angles are small, or these deflections are small, both of them actually, then the rho is typically very large. We're talking about large radii. Now, in this case, if we have this concentrated moment, okay, being applied, right, we've seen this shear force and bending moment diagram like this. When is the curvature positive? Over here, right? Because this is when the bending moment is positive. When is the curvature negative? Over here, because the bending moment is negative. And if you look, right, that's what you would see. What are you going to see? You're going to see like a little hump right here, right? It's going to go like this, and then down here it's going to go like this. Okay? So we can use these relationships to kind of see or describe what we already know, kind of by our intuition, right? This is what it's going to look like. Now, we still have not, that's very nice, right? We still have not really figured out what deflection is relative to this phenomenon, or these phenomena, right? So, what about deflection? If you go into your calculus class, all right, this definition will appear, right? The curvature is equal to the second derivative, okay, over this 1 plus quantity first derivative squared to the 3 halves. Okay, we're not going to rederive that, but that's the definition of radius of curvature. So now we can do some substitution. What is 1 over rho? 1 over rho we determined was 1 m over EI. And the slope of dv dx is small for our cases, so dv dx is in the denominator, right? But luckily there's a 1 plus it, all right? So this is dv dx, and a small thing squared is a very small thing, so this is going to go to 0, and then we have 1 plus this thing, and that's so you end up with this expression. So this is now the expression we want. And usually we write it in terms of this. M equals EI, second derivative of V with respect to x. It gets better. Because how do we relate m and v to each other? Well, dm dx is equal to v, remember? So now we have a third derivative, okay, that relates the shear force, big V, to the deflection, little v. And we have another derivative that relates the distributive force applied to the beam with the fourth derivative of deflection. And you're like, do I really use these? Yeah, you can. Okay, now there's some strategies here, but this is, but these derivations, you know, lead us to these big equations. These are the three that, these may be, are these the final ones? These may be the final equations that you include on your formula sheet for the exam. Okay. There are probably some others, you probably include an exam work too, right? But these are kind of the big three. Okay. So, just remember that we're talking about vertical deflection. Okay. And we have EI, which is sometimes referred to as the flexural rigidity, and you have distributive force, and you have internal shear force, and you have internal bending moment. Okay. So we've gotten very good, right, at figuring out what M and V are across the beam. What do? We use that information then to figure out what the deflection is. So if we didn't do enough integration already, we get to do even more integration, okay, with differential integral relationships. What do I mean by that? That means that if I have M, I can take two integrals to figure out what the deflection is across them. But if I do two integrals and they're indefinite integrals, what do I need? Yes?
Constants at the end.
Right, you need constants. You need more boundary conditions. So what are those boundary conditions now that we can use? Yes?
Like if we know when n's 0, what value it is when it's 0, stuff like that.
Okay. So this assumes I already know what the bending moment is across. Okay. And I already used my, my internal shear force, my internal bending moment, I use those force moment relationships to figure out those boundary conditions. So what do I have to do now? It's worse. I have to use, not worse, this is all happiness. Now, remember we said, look, the slope for this boundary condition, right, if I come out of a wall, the slope of the displacement versus x is 0. The v is 0. Those are the new boundary conditions that I'm going to be using. At a pinned joint, I know my v is equal to 0. I have no deflection, but my dv, dx there could be something else, right? Those are the types of boundary conditions we're going to be using. Okay, so here we go. Oh boy, I'm going slowly. Okay, and I don't want to keep you guys too late. So we'll get through this, and then I'll make the FEA not due tomorrow. Okay, you can turn that in for the last assignment. It's not that hard. We'll do it quickly tomorrow morning, or tomorrow, whenever we do it. It's not that bad. Okay, it's easier than the pre-Comax. Okay, trust me, because we're not going to use pre-Comax. Okay, so here, this is just doing the math. Okay, there's no geometry given here, but let's just say that you have omega or wx is equal to minus w naught. So you're like, okay, I actually know what that geometry looks like, but let's just do the math for a second. And I have at x equals 0, the displacement is equal to 0, x equals L, the displacement is equal to 0. I know I have v of 0 is equal to w naught L over 2, and I have m at 0 is equal to 0. So I have all these boundary conditions and I have my w. What do I do based on what we just said? What do we do? Well, if I'm given w, I start right here. How many intervals do I have to do? 4. Alright, so here we go. I write it out. I do one integral. Or I first write that out. So here's the integral, alright? And I have a constant. Alright. And this is a this is interesting, I guess you could say. We can remember though that this third integral is equal to v of x, right? And what do I have? I have this boundary condition right here. Okay. So now what I can do, I can solve for C1 with this boundary condition. So that's the boundary condition, and that is going to be C1. Cool. I do it again. Integrate now. Okay, so we have, we could have plugged this in, whatever, but that's a C1x plus C2. Okay, and will we remember? This term is equal to the moment. And I've got I've got this one, but I'm not sure what to do. Because like, oh, they gave me v of 0 is equal to 0 and v of l is equal to 0. But they didn't give me, I didn't give us dv, dx. So, what do? I just proceed. I do one more integral. I have a c3x and I have a c4 now. But now I have two unknowns and two boundary conditions. And so I can figure out that c4, right? If I plug in little v of 0 equals 0, that means that c4 equals 0. Okay? And then I can plug in v of l, right, into this equation and set this equal to 0. And now I know what c3 is. Okay. So the math is not that hard. Yes?
Where did the v of 0 equals 0 come from? Oh, gotcha.
Right there, right? This is just to show the process on the map. Okay, just to show the map. Now, you people are smart though. What does this system really look like? Yeah.
Is this just a cantilever with a distributed load?
Well, is it?
No, it's not.
We have m of 0 equals 0, which means it can't be a cantilever beam, right? Because that would mean that because the cantilever beam has to have a bending moment at that left side or right side, whatever, right? So this is probably, right? But I know that the deflection is equal to 0 on both sides, so this is just a distributed load on pin.
Yeah.
Okay, or pin roller. Okay, so what's next? Come on. Let's finish up okay, so this is that final expression. And sometimes you'll see people just leave the EI over here. Sometimes they do 1 over EI, right? It doesn't really matter. Unless I say expression for V, then just please multiply the right side by 1 over EI. Okay. Yeah, so this is the configuration we were talking about, okay? Like this. Okay, yes, I can do all that just to show you, okay, this is what it looks like, all right? And this is what that V looks like. Now, when is V of x a minimum? Well, I take the first derivative, right, and I set it equal to 0, so the slope is equal to 0. But I already did that. If I look back, right, I already figured out what the first derivative of this thing is. It's right here, dv dx, right? So I can set that equal to 0. Okay, and that's going to be, that's going to tell me that this happens at x equals L over 2. Okay, and that's when it's going to be a minimum. You know, it's also probably good to notice that by our convention, these expressions, this v is going to be negative as it goes across, right? It's going to be negative, all right? So down here it's going to be a minimum. It's going to be, you know, most negative. All right, so question 1, you'll get to do something similar, all right? And here's the procedure that I would like you to know for the homework and for the exam. You're going to get a general idea of what the elastic curve should look like. You're going to break up the beam into regions with neighboring discontinuities and applied loads or boundary conditions. You're going to find the necessary expressions for moment, shear, and or distributed loading. Okay? So those are, you know, it's kind of going all the way back to how you do the bending moment diagrams and shear force diagrams. You integrate twice for moments, 3 times for shear, or 4 times for distributed loading, making sure you keep adding constants in the steps of integrations. So you have choices. You can start all the way from EI, fourth derivative, is equal to W. Often though, right, it's makes more sense if you can start from the equation on the top right, where you have EI second derivative of V with respect to x equals an m. Okay, that's usually where you want to start. But you can start from here if you need to. Apply boundary and continuity conditions, and then you're going to determine the expressions for slope, angle, theta, and vertical displacement v. All right, and I didn't point that out in that like algebraic one, but that dv dx, that was theta. Okay, this is dv dx. Okay, yes. Okay, breaking beams into regions. Keep track of the direction of x and sign conventions. This is important. Okay, so you have multiple options. You could say, I'm going to have x1, okay, and then when I hit this continuity in applied force, I'm going to have something that I use to describe this region in here, and that would be x2. But my x2 is actually relative to the left side. Algebraically, this is probably more headachy, okay? So there are alternatives. And one alternative is to define an x2 that starts where that discontinuity is applied. Okay. Another option is to define x2 coming from the right, and then they meet where this discontinuity is. Okay. So you have options for where you apply this. Now, remember, we have rules about conventions, okay? And so you have your M's and your V's and your V's and M's and all this stuff, right? So just remember as you're coming from each side. But there's also now another thingamabobber that we have to keep track of. Before, we had to keep track of internal M's and V's and using our conventions, right? Because if you have a slice that exposes the left side versus a slice that exposes the right side, you know, your V and your M are going to be in opposite directions. One thing that happens, okay, is, can you see here that this is a positive slope? dv dx is positive. Anywhere on this, you see that's positive? If I'm coming from the left, right? That's our way of thinking. I'm coming from the left. Coming from the left, my slope is positive, like that. Okay. But if I come from the right side, right? Now I'm coming downhill. I'm going downhill, so my slope is actually negative. So this is something you gotta keep in mind, all right? That if, and so you see, well, this is, you know, so this is also a positive slope when x is coming from the right? It's going up like this. So both of these guys have positive slopes, right? But once I get into this territory, right, if x gets into this territory, then it's a negative slope. And if I get into this territory, then it's a, you know, and they're connected, then it's a negative slope. Okay, so at these locations where we have discontinuity, all right, so here, okay, v1 of d is equal to v2 of d, theta 1, okay, because, you see that, they're equal to each other. Here, okay, again, v1 of d, all right, so here, this is the v1, so this is associated with x1, okay, is equal to v2 L minus d, all right? So if we have a displacement that we're defining that's coming from this side, okay, L minus d is how far the p is, okay? So we're saying it's not necessarily in the middle, right? If it's in the middle, then, you know, it's just L over 2. But let's say that p is not in the middle, then yes, the displacements are the same. But, and this is the biggie, the slopes are opposite. You see that? Like we were talking about here, right? This is positive. Okay, so look, it was negative, 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 negative slope. But if I come from, or yeah, you know, I'm going negative like this, right? Whatever that quantity is, if I come from this side and I start going up this, you know, I go up this area, right? Then it's positive. Similarly, if I'm past this point P or wherever it is, right, this is positive, 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 and but I come from the right side, it's negative, 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 negative. Okay, you see that? So where these two coordinate systems meet, if you've calculated out the theta 1, you know, from one direction, it's going to be negative that from the other direction. Yes, Andrew first, and then.
Yeah, why do you have a x1 and x2? Like, why not just one plus 2?
Because you don't usually do it this way, right? Usually I would do an x2 from that location, right? So, you know, maybe a more common thing would be that x or v1 at, let's say, the midpoint, if it's L over 2, or v1 at D, right, is equal to v2 at 0, right? If that were, you know, a more common way is to say this is x2. That's the more common way to do it, okay? But you can, but nonetheless, it is possible to find another x2 from that same location out here. Okay? They're going to have different properties. Okay, because as you hit this region here, you're going to have a different expression. Okay. Okay, so boundary conditions. Whew. All right, so boundary conditions affect shear force, bending moment, vertical displacement, and slope. All right. So I think I kind of already described this a little bit, but the roller or pin at the end of a beam has 0 displacement and m equals 0. The fixed end has v equals 0, theta equals 0, okay? And we know that the m is not going to be necessarily equal to 0, right? And that the force, that you could have a reaction force there, okay? The free end is just that the shear force and the bending moment are equal to 0. Okay? So maybe this is the last, I don't know, you know, there are multiple things you want to put on your notes, you know, for the exam on Thursday, but these are some of the big things to keep in mind. We already knew this. This is not new news. This is also not new news, but these 3 relationships are maybe on the newer side. Okay. All right. Okay, so you can take a look, all right, at this example and the notes. It's there. All right. I'm just out of time, unfortunately. Okay. But once again, we do a bunch of integrating. You know, maybe not too much integrating in this case because we already know what the bending moment is internally, so we only have to do 2 intervals. Okay. But we're coming from the left and the right side, so we're going to have a theta 1 equals minus theta 2 at the middle where that p is being applied. Okay. And you do some more integration. Okay. And we can, if you have questions, okay, and this is just showing you can do something slightly trickier, but be very careful with this. I've made mistakes on this, where I say, oh, by symmetry, I'll just say that the theta here is the same. Or I'll even go further to say that theta is equal to 0, right? That's what we've done here. Okay, but be very careful with this idea. Because, like, I tried to do that here, and that was a bad idea. You have to do it. Like, I thought theta would be 0 at L over 4, okay, but it's not necessarily that. Okay, so question 2 is a doozy, but thanks to Michael Grossi, previous student, you have his notes. This is one way to do it, okay? So look through it, and you'll be in good shape. And then next time, we'll do finite element. Any questions? Any questions? Yes, Andrew.
Wait, so did the theta 1 represent theta from the x1 direction? Is that
Yes.
what it's
Yes. Yes.
Okay.
Yes. So when we say theta 1, like here, yeah. Yes, we're saying that's coming from the left side going that direction. And so normally you would say that's equal to minus theta 2, right, coming from the right side. But since it's equal to, they're both equal to 0, it doesn't matter, right?
But at any other distance, there would be a negative sign.
Well, at any other location where it's non-zero, really. Right? In this case, I'm making an assumption that when it bottoms out, which is not a bad assumption, right? Because we said when the displacement is minimum, right, or maximum negative, right, that's the first derivative is going to be equal to 0. And the first derivative is equal to theta. Okay. So a safer approach is to use, like, using symmetry, unless I tell you to use symmetry, well, you gotta be smart, I guess, but this is the safer approach, right? Where I say v1 is equal to v2 there, and theta 1 is equal to minus theta 2 there. Safer approach, but more algebra. Because knowing that it's 0 speeds up things a little bit. What are constants? Okay, other question? Did you have a question?
Haven't read that, the kind of to
Okay.
part enough to ask a question.
Okay.
I had a question before, but it was answered.
Okay. This is pretty tricky stuff. Okay. The good thing though is it's all about the algebra or the calculus, I guess. Okay, then what we talk about tomorrow, when we go beyond the FEA, that is a little bit more tricky, shall we say. Like, you have to see it a little bit more, but that's not going to be on the exam. Okay. Well, thank you, and we'll go ahead and close if there are no other thoughts or questions. And I'll make sure that the FEA is not due tomorrow.